Okay, we will go ahead and get started. Today we're going to explain a term I used on Monday and a term which appears in Lab 7. And I want to go through about how I've been lying to you about how memory in Python works, but that's okay. It's been an similar explanation, and now we're going to dig deep in the details. The first thing I want to start with is something I've talked to a number of students about Project 1. Remember, you have until next Monday night at midnight. A number of you were having problems because some of the data files may have extraneous new line characters at the end. That is, there may be an extra new line or two because of the way I saved the text file. It really seems to depend on how you load the text file into your system, whether it be PyCharm, GL, whether you copy and paste it from GitHub or whether you download it, whatever. So what I want to do is make you aware of that, if you haven't run into it already, that there may be an issue with list sizes because of these extra new lines, and we're going to talk about how to get rid of them. So hopefully, if you're having this problem, this will solve it, since this was never supposed to be part of the challenge of Program 1. So a couple of them have extra new lines, and so when you split, let me fix that typo. When you split the file on the new line character, you wind up with one or two blank rows at the end of your list, and that can cause you problems later on when you try to split the blank list and get the actual project scores out of them. So there's a couple of ways to get rid of the blank lines. We're going to go over them right now. Let me go to PyCharm. What I've done here is I've just got a simple routine, sort of like read file. Now, when you write the function read file in Project 1, you're going to pass the file name as a list, as a list element. Here, I just coded it. I'm going to read fall 2021. This is the fall 2021 data. It's the physics and chemistry Nobel winners. And the way I've done it here, as an example, you can see there's actually a couple of blank lines. There's actually two extra new lines. Okay. So when I run it, when I read in this file, I'm going to read in the entire thing. And I'm going to split on new line. Now, in this case, I haven't worried about getting rid of the extra two lines up front of headers. You know how to do that. That's not important. I'm going to split on new line. So let's do that real quick. We've read in the data, just as you'll do in Project 1. And then we've split the file on new lines, just as we'll do in Project 1. Now let's look at what the contents of this split list are. Again, I didn't get rid of the first two lines in this one. Don't worry about them. They're not relevant. If I look at the end, what I see is, because of the way I prepared this data file, there were a couple of extra new lines in there. And so the result is I get a couple of extra blank lines. I have something that's actually 2 students too long. When I ask for the length of this, how many rows do I have? You can see I have 24. There's only 22. There's only 20 students in that class, plus the 2 extra lines. There should only be 22 lines here. There's 24. So if I do things based on the length of this list, based on the number of rows, I'm going to be wrong. I'm going to get errors because it's too long. So here's how, if you do get extra blank rows in some of your files, here's how you get rid of them. And we'll explain why during today's lecture we do it this way. We simply create a new list. We'll call it D2. It's an empty list. It's an empty 2D list, but we have an empty 2D list the same way we have an empty 1D list set of characters. And I go through my original list, D1, and for every row in it, I check to see if there's anything there. If it's just an empty row, if there's nothing there, then the length of D1 sub I, the length of that row, is going to be 0. If the length of that row is 0, I know that's an empty row. That was just extraneous. I don't want it. So if the length of the row is not 0, I'm going to append it to my new list. If the length of that row is 0, I'm not going to append it, which means I'm simply, in effect, throwing it away. So when I run this code here and create D2, now if I look, you'll see down at the end, the last row is all of these students. The last row is actually the last student in the class, Peter Higgs, who hypothesized the Higgs boson, if you're into physics. Okay. So in this case, what I've done is, because of the way the file was prepared, there wound up being some extra new lines, not extraneous, not relevant to the file, to the problem. But if I used them, if I left them in, then I might have a problem, because the length of my 2D list, my number of rows, is too many, and I'm going to have a problem. Okay. So if you have that problem with your data files, either on PyCharm or on GL, you may use this code or other code if you want to get rid of them. Okay. This code, there's other code if you want to get rid of it that way. That will get rid of those extra blank lines. Because again, the fact that the extra new lines were there were not originally part of the programming problem you're supposed to solve. That's kind of an extraneous issue. So this is how. And yes, since I gave you that code, you are permitted to use that in your project one if you need to. Feel free to do it another way if you want. If you have a better way to do this, that's fine. But this is just something that, in talking to a couple of students already, I've noticed people are having problem with. Here is how to solve that problem, or one way to do it. Okay. The extra blank lines appeared because there were a couple of new line characters at the end of the file. Maybe. Doesn't always happen, but it maybe. It depends on how you create the data file. Here's how you get rid of them. Now, why did I do it that way? Okay. Here is what some people call the bottom line up front. This slide appears at the end of this lecture as well, but I'm going to put it up here. This is the spoiler alert slide, or if you prefer, the bottom line up front. This is what you should take away from this lecture. You should leave this lecture today understanding the following. There are two terms we use to describe variables in computer science: mutable and immutable. Mutable means that its value can be changed after creation. When you create a variable and you assign it a value, if it's mutable, you can change that value. If it's immutable, you cannot change the value once it's created. Now, here's where it gets confusing, and I know this always causes problems for students, so we're going to try to work through this with lots of illustrations and lots of examples and lots of patience, because this is a bizarre idea, and Python did this differently than many other languages. On Monday, in that lecture, I told you that if you had a dictionary, the keys must be immutable. And on Monday, I said, don't worry about what immutable means. Just, it could be ints, strings, floats, or booleans. Okay. That's because in Python, simple types, ints, floats, booleans, and strings, are immutable variables. Now, that sounds wacko. That just sounds completely strange. We're going to work through, and I'm going to convince you that you're not going out of your mind. That really is the truth. Complex types, lists, and dictionaries are mutable. Lists and dictionaries are mutable in Python. They can be changed after they're created, but ints, floats, booleans, and strings cannot be. They are immutable. That means that ints and lists behave very differently when you make assignments. If you start making assignments in Python, an assignment to an int behaves very differently than an assignment to a list or assignment to a dictionary. And we're going to give some illustrations about that. if you're not careful, you can accidentally change the value of a mutable variable without wanting to, without meaning to. So you have to be careful. Let's go through that. Okay. Python variable strangeness. Let's go to Python. I've got this all loaded in. I've got very simple code. A equals 1, B equals A, add 1 to B, and see if we've changed A. Well, of course not. We haven't changed A. We made a copy in B. We added 1 to B. We haven't changed A. Why should this be any different? A should still be 1. And in truth, that is exactly what happens, right? You know, A is 1, B is A, B is now 2, but A is just 1. B is 2. This works exactly like you would expect. Immutable variables work exactly like you would expect. But now, let's try a mutable variable. A list. Same thing with a dictionary, and I'll talk about Lab 7 in a minute. C is a list 1, 2, 3, 4. Now we know that's a mutable variable, just because we've said so. D equals C. Now I appended 5, the integer 5, to D. I did not append to C, I appended to D, and D is supposed to be a copy of C. But when I went to print C, lo and behold, the 5 got appended to C. How on earth did 5 get appended to C when I appended it to D? The reason is that the way Python deals with this assignment statement, B equals A, and this assignment statement, D equals C, is very different. Let's go back to the slides for a minute, and then we'll come back to PyCharm and illustrate this some more. This is just variable strangeness. This can, if you're used to programming in a different language, this can be bizarre. If you're not used to programming at all, for now, just bear with me. I'll try to prove to you this is how Python works, and it actually sort of kind of makes sense. Here is the same drawing of memory I've been using throughout the semester. Okay? Memory is just a list or group of places to store things. And we have a symbol table that assigns things to them, to these locations in memory, to store values. In my program, when I said A equals 1, Python went and found an empty location in memory and set the symbol table to say this location in memory is going to be A. Cool. When I said B is equal to A, because these are mutable, because these are ints, Python went and found a location in memory, another one, a separate one. These are immutable variables, ints. Okay, make sure I said the right thing. I think I didn't. Okay, Python for B found a separate location in memory for B and copied the value of A into it. So when A was 1, we found another new location in memory and we said, copy the value from A into there. B now equals 1. Now my next statement, B plus equals 1, changed the location of that, changed the value of that location in memory, the one associated with B. It left A the same. Okay, maybe need to make this a little bit clearer. A equals 1 puts a 1 right here. B equals 1 gets another new location in memory and says whatever the value is up here, copy it down here. Put a 1 down here in B. Okay. Now my statement b equals b plus 1, b plus equals 1, changes that 1 to a 2, but leaves a alone. So when I said print a, I got a equals 1. This makes sense. This is cool. This is normal. This is the way an immutable variable works. On the other hand, for mutable variables, and I try to be careful, I accidentally say this wrong several times. For mutable variables, Python doesn't get a new location in memory. It just copies the old one. So I created a list C. List has the values 1, 2, 3, 4. When I had the statement in code, D equals C, unlike over here, Python did not go get a new location in memory and set it to D and copy this value. Python just said, okay, D points to the same location in memory as C. Okay. D points to the same memory location as C. That is the difference. Immutable variable, ints. When you say B equals A, Python gets a new location in memory, copies the value, and now you're working with a copy. When you have a mutable variable, either a list or a dictionary, when you say D equals C, Python treats it differently. Python says D points to the same location in memory as C. That's why the next line of code in that list example says append 5 to D. Okay, cool. I did, in fact, append 5 to D, but notice, because it's the same location in memory, I appended 5 to C at the same time. This is why when I then printed out C, C has 5 in it. C has 5 in it because it was the same location in memory. And when I appended it to D, I appended it to C. So, mutable means it can be changed. And in fact, the value of C was changed by adding 5 to it, by appending 5 to the list. Even though I did it through D, this can be changed. Now, that's most of the problem. For now, believe me that if I have an immutable type, assignment and copying works like this. If I have a mutable type, assignment and copying works like that. And so they're fundamentally different. Okay, but what about this? What about A equals A plus 1? Wait a minute. Why doesn't that take this value and make it a 2? And now A equals 2. In fact, it does not. Here is what really happens, and I'm going to show you this in PyCharm in a minute. When I say A equals A plus 1, make that a small a. Here's what happens. Python says this is gone. Okay? Python says this no longer is A. Python says let's get a new location in memory. Call it A. And assign the value 2 here. So Python, in the symbol table, actually assigns the value of 2 to this location in memory. This location in memory is now A. This location in memory is no longer used. It's gone. So when we say if you have an integer variable in Python, it is immutable. It cannot be changed. this is what it means. The value stored in this location in memory cannot be changed. If you change the value of this variable, you will get a new location in memory, and the new value will be put there. And then if I said a plus equals 1 again, I would get yet another new location in memory, and the new value would be put there, and this would be thrown away. It would now be marked as unused. We can never change the value assigned to this location in memory once we have assigned it, because it is immutable, and immutable means cannot be changed. Okay. On the other hand, mutable variables like dictionaries and lists, those can be changed. I can append 5 to this list. I can remove 3 from this list. I can do whatever. If this was a dictionary, I could do the same thing. If I had a dictionary here, I could add a key, or I could add a value, or I could delete a key, or I could delete a value, because it's mutable. It can be changed. All right, we're getting more and more bizarre. We're getting into wild things. This slide just talks about what I just said. Immutable, cannot be changed after being created ever for any reason. This statement does not change the value of that original location in memory. Okay? Here, let me just go back to Python before I get to these charts. A pie chart. There is a function in Python called ID. ID shows you the location in memory of a particular value. So let's start with a equals 1. ID of a says, show me the location in memory of a. A is at location on my Mac 450-9977280. This is meaningful only right now for this program on this computer. When you run a program, your memory locations are going to be different for every type of computer, and even on the same computer, your memory locations are going to be different for every time you run the program. So we do not, at this level of computer science, worry about those memory location values. We just don't care. When you get higher up, if you get into an operating system program, if you really get into cybersecurity and people trying to hack your computer, you care about them. But at this level, we don't care. They just are the values. Okay, that is the location of A in memory. Now, B equals A. What's the ID of B? Okay. That's interesting. It's not supposed to do that. It gave me the same thing. Okay, I got it. Okay, we're just pointing to the same location for now. Now I do B plus equals 1. What's the ID of B? Notice that originally B had the value of 1. It was in this location in memory. When I added 1 to it, it threw away that location in memory, and it gave me a new location in memory. Now, in this case, if you really care, it turns out that the way the Mac works, it's going to give me 32 spaces, 32 words up in memory is where the new value is going to go. For integers, it's going to bump me up by 32, typical. If I do B plus equals 1 again, and then do ID of B again, it's going to have bumped me up another 32. Not relevant, just an interesting, show off. This is what we can do. Okay. So A and B, different locations in memory. When we change the value, we change location in memory. This is why this statement, where's A? A is still here. B is here. These are different. Changing A, changing B do not change the other one. Now, let's go to our list. The list of 1, 2, 3, 4. Where is C? Okay. C gets an interesting, different location in memory. Why is it so much different? I haven't got time for that. It just, for now, it is. It's in a different location in memory. Okay. Don't care, except that it is. D equals C. Show you, as I've said, that D is the same location in memory as C. Now, D dot append 5. What's the value of D? 1, 2, 3, 4, 5. What is the ID of D? It's the same as it was. The ID of D, the location in memory of D before I added something, was here. When I added something to it, it's still the same location in memory. Okay. Same thing with C. C is still the same location in memory. So when I change D, I change the value of this location in memory. That is still the same location as C. And therefore, when I change D this way, I in fact change the value of C. A mutable variable, like a list or a dictionary, when I change it, the value before, location of memory before, and the location of memory after are the same, and I have changed the value of that location in memory. With an immutable variable, like A and B, every time I add 1 to B, I get a new location in memory, because Python says, uh-oh, I can't change the original value stored here. That's ints are immutable. That is immutable. I can never change that. So when I want to add 1 to it, when I change the value, I have to get a new location in memory and assign the new value here. So that is what's going on. Symbolically, or the computer science theory behind it, I've told you all, this part I told you is true, is that there really is a symbol table when your Python program's running. And the symbol table says what identifier, what variable name, what constant name, what function name did Al use? Al used A. Al used name. Al used read file. The symbol table says A is an integer, and here's where it is on some other arbitrary run of the program I did. On some other program I ran, it said name is a string, and here's where it is in memory. And when I define my function read file, to read in a file for project 1, it says, it creates an entry that says read file is a function. When he says read file, I'm going to go to this location in memory because this is the location that contains the code. Okay. This doesn't tell you the value of anything. It tells you where to go look. So when your program uses A, it goes to the symbol table and it says to get the value of A, go here. When you use the function read file in your program, it goes to the symbol table and says, what's read file? And the symbol table says, read file is a function, and it's at this location of memory, go here. That's all it does. Okay. Here is my description of what ID does. We don't use it in this class because, as I said, at this level of programming has limited usefulness. If you're taking operating systems theory, or if you're taking detailed cybersecurity or whatever, you might get into it because you care about locations in memory. But at this level, we don't care. I'm using it as to illustrate. And the reason, as I said, is because if I run this program a different time, it's going to get a different location in memory. Every single time I'll get a different location of memory. And if you run Windows and I run Mac and somebody else runs Linux, we're all going to have different things as well. So we're just not going to use this except to illustrate how this actually works. Now, some of the stuff I've already shown, and I've got all this in pie charts, so I'll just walk through to illustrate stupid programming tricks. Okay? I'll use ID to show you that when I define an integer, A, give it a value 1, it has 1 location in memory, and when I then add 1 to that, it's going to come up with a new location in memory. Okay? Yeah, all right. Let me do this again. A equals 1, ID of A, that value, A plus equals 1, ID of A. It's different. Okay, it's giving me a new place. And you'll notice this looks like it reused the addresses from previous because since I redefined them, the old memory locations were available. So it said, why not reuse it? Now, B equals A, ID of B. Going to point to that location in memory where A is right now. B plus equals 1, ID of B, not D. And we changed. We got a new location in memory. List. X is an empty list. Where in memory is X? It's over here. X dot append 1. Let's put 1 in our list. ID of X. Same location in memory. I can change the value of a list without changing its location in memory. I cannot do that with an int, mutable versus immutable. X dot insert 1, 2. X is now the list of 1 and 2. Different. ID of X, same location in memory. Okay. Immutable doesn't change. X now becomes the list 1, 2, 3, 4. Okay. Now it thinks this is a new assignment. This assignment is a new variable. This is not modifying the previous list. This is assigning a new variable. This is assigning a completely new variable, and I'll explain in some examples why that's important. Okay. This is what we already did. I'm going to skip that one. Here is another one that I have on there that I want you to see. I'm just going to run a loop. X is 1 through 10 times. I'm going to add 1 to X, and I'm going to print out the location of X. And you'll notice that the location of X changes every time through the loop. Every time I change the value of an integer, I throw the variable away and get a new location in memory and come back. So all I've done with ID is try to illustrate what's happening. Here is the impact on your programming. Okay. This is just a note. I'm going to skip this. This is just a reminder. We've talked about lists already. You can't, I'm sorry, strings. Strings are not lists. They are like lists some ways, but they are different. One of the ways they are different is that lists are mutable. Strings are immutable. If they allowed you to change a value of a single letter in a string, that would modify the value of what's stored in memory, and that would make strings mutable. But that's wrong. That fails. Okay? That fails. So therefore, strings, because they're immutable, that's one of the ways they're different from lists. You cannot change individual elements, individual characters, individual letters in a string, because a string is immutable and cannot be changed. You can have a new assignment. You can start with the state Maryland. You can then have a new assignment, which will get you a new location in memory to have a different string. You can do that, but you cannot just change the first letter. Okay. This is a new assignment. It creates a new variable. The fact that you have the same symbol in the symbol table is not really important. It's a new location in memory. It's a new value. Okay. But we can still read individual letters in a string, yes, because they don't change the value of the string. if you don't change anything, mutability is not important. And in fact, you can read the same location in memory all the time. You can read the first few letters. And in this case, what I've done is just have a string. And if the first 4 letters of the strings, Maryland, spell out Mary, then I print yes. And in fact, it will, of course. You can read in letters of the string and use them as slices in your code, but you cannot change them, and you cannot change them because strings are immutable. Okay, let's try to work through this some more. Again, what's really happening in memory, I showed this earlier, but I go over it again. A equals 10, in new location of memory, stuff 10 there. A equals A plus 1, A plus equals 1, immutable variable, integer. Python says, whoa, get rid of this location of memory, doesn't exist anymore, get a brand new empty one. 10 plus 1 is 11, put 11 there. The old location in memory is gone, it's unused, it's available for use next time the program wants it. What happened? Mutable variable, not the case. You do not change locations in memory, you just work on the one you got. Okay. Shoot me a second. Why on earth would anyone ever create a Python, a language like Python? Why would you do something like this? And no, this is not something that you're ever going to see on a test. I just want you to understand why it was done. It was done on purpose. It turns out that when you actually look at what's happening in the language, in the computer system behind the scenes, immutable objects, immutable variables are much faster to access when the program is running. You can put in shortcuts. You can make the operating system memory management work in such a way that it is much, much faster to access an immutable variable than a mutable one. Okay. So you want to use an immutable object whenever you can to speed up your program. Mutable objects, because you can change them, it turns out it takes much, much longer internal to the operating system to access them, and it slows down your program. And so the designers of Python said, here is a design trade-off, right? Our design trade-off is that we will make ints, strings, booleans, and floats immutable because they can be accessed really, really fast. We will make lists and dictionaries mutable because history of programming, as examining thousands and thousands of different programs, shows that almost all lists and dictionaries get changed during the program execution. You don't have a list or a dictionary unless you're going to change it during the execution of the program. But a whole lot of times in programming, you don't change an image. You don't change a string. You don't change a float. You don't change a Boolean. Sometimes you do, but a vast majority of the time in your program running, you're not going to change things. And so you write a programming language that says these things, which mostly don't get changed, get implemented in the fastest possible way. And these things, which mostly do get changed, get implemented in a slower way, but an easier to change way. This is not on a test. You never have to remember this after tonight's lecture. But for those who are curious, and I always get a couple of questions on this, why? Why would you do this? This seems confusing. This seems strange. Why would you do this? You do this because this is a good design trade-off between speed of your code and making things more complex and confusing the heck out of your programmers. It's a decent trade-off. And Python's success indicates that, yeah, it probably is. Okay, that's why it was done. No, you'll never have that on a test. But it's just, if you're curious, that's why. Okay. Immutable objects in Python. Ints, floats, Boolean strings, tuples in Unicode. Don't worry about those. We're not going to get to them until much later this semester. But in case you ever do see one, those are immutable. Mutable objects are list, dictionary, and set. If you take another Python class, I think it's comp sci 271, 271 or 291 is the advanced Python programming. It's the second course if you want to take it. Then you'll get into using sets. Sets like lists and dictionaries are mutable, okay? And the assignment statement means that you get the same address in memory, you point to the same location, and you can change it. Okay. Now, passing a list to a function. This is almost what Lab 7 does. Lab 7 passes a dictionary. We'll talk to that, I promise. Okay. So, when you're passing a list as a parameter in your program, which, by the way, you're going to do in Project 1, right? You're passing lists around to various functions. Here's my function, and here's my main program. Now, in the main program, I have a main list, 1, 2, 3, 4. I call my function strange stuff, passing this as the argument. So it gets mapped to a list. This is the parameter. Then I append 5 to the list, and I return, but I don't return anything. So remember, if I don't return anything in my return statement in my function, that means I return the special value none. I return none. So nothing down here changes the value of my main program main list. But in fact, main list has been changed. Main list is what was 1, 2, 3, 4. Now it's 1, 2, 3, 4, 5. The reason for this is mutability. When I pass a list as an argument to a function, that parameter value gets mapped to the same location in memory. So when this function gets called, this parameter, a list, points to the same location in memory as main list. So let's write that same code, except we're going to change it. Let's print that directly. Okay, and now let's run the function this way. Okay, sorry. That's because that's supposed to be a parenthesis, not an underscore. There we go. What did I do this time? Okay, hang on. I have unbalanced parentheses is what I did. 3 and 2. Okay, that should have fixed that silly problem. Never ever try to do a live demo. Here we go. Balanced parentheses, underscores, everything appears to be correct. There we go. All that time to illustrate that this is the identity, this is the location in memory of the argument. And this is the location in memory of the parameter, and they are the same. So the locations in memory of the argument and the parameter are the same. And thus, when I modify in the function the parameter value, when I modified a list here at the same time, I modified main list down here. Okay? That would not work the same way with an integer. def. More stuff. It's going to take an integer parameter b, and I'm going to have to fix that typo. Print ID. Let's see. I'm going to return none. What did I call that function? Okay. Let's see if I can manage to get this running the first time. Okay. What I'm illustrating here is that I did a similar thing with integers that I did with lists, but the parameter in the function and the argument in the main program are different locations in memory. And so when I change the parameter value, it does not change the value of the argument in the main program, okay? Because those are immutable variables and they work differently. Now, that's a list. It works exactly the same way with a dictionary. Let me go to Lab 7. So when we talk about Lab 7, the function you have to implement, I'm not sure how well this is going to show up, but the function add favorite number takes a string who, an integer number, and a dictionary favorites. Now, who and number are immutable variables, so we're not going to ruin what we have in the calling program, the main program, or another function. Favorites is a mutable variable as a dictionary. Thus, whatever was called, in other words, whatever called favorites is going to refer to exactly the same location in memory. And so when I modify favorites in this function code that I write, it's going to modify the main program. And so that is the comment down here. Apologies if this isn't sharing very well. But the comment in the code we gave you in Lab 7 says, return none. Dictionaries are mutable, so you do not need to return it to modify it. So in other words, we could have returned the dictionary favorites, right? We'd have had to change how the function is called, but we could have done that. We did not do that because we didn't need to, because we know that since this is a mutable variable, we are changing it in the function. We are changing the value of favorites in the function call, so we do not need to return it to modify it in the main program, so we return none. That is what this statement in the Lab 7 assignment says. Okay, it is a mutable variable, therefore we can change it in the function. The change will be reflected in the main program. We don't need to return it. That's all that means. Okay, so in the code I showed you here, I illustrated doing that with a list. I modified the list in the main program by doing things in the function, so I didn't have to return some value associated with the function to make this work. With an integer, with an immutable variable, you have to return it. So laying out your code design, you have to think about, are you returning a type that's mutable or are you returning a type that's immutable? Okay. You have to think about that because when you're looking at project 1, sometimes you're returning an immutable type. The function read file, read underscore file, returns a string. Strings are immutable. Okay, so you're going to have to return the string to make things work in read file. Create list, you're going to be returning a list. And then other things use lists. So you may or may not have to actually return the value. Now, it does not harm anything if you explicitly return the value, even if it's a list, even if it's a dictionary. As long as you're at code right, you can do it, but you don't have to. If it's an integer or a string you're returning, you must return it. Again, why? Bluntly, because the guy who originally developed Python is a Belgian guy named Guido van Rossum. I think he's Belgian, might be Dutch. I think he's Belgian. He originally wrote Python. Right now, Python is written and maintained. It's open source. It's free. It's written and maintained by a very large group of people. But the guy who originally wrote it, Guido van Rossum, thought it should work this way. And guess what? Enough people agreed with him that Python caught on. I mean, if people thought he was completely nuts and should never have done that, then Python would not have caught on. He'd have had to change it. But he thought it should be this way. And okay, if you want to have a programming language that works differently, write it. If you write your own programming language, you are now in control. But what if I don't want to mess with the list? What if I just want to work with a copy of the original list? I don't want to mess with my original list because I don't want to mess it up. It's my only copy. Okay. You have ways to build a real copy of the list. Okay. You can use a slice or you can use a list constructor. Okay. So let's go to PyCharm and see those. Okay. So C is once again my good old-fashioned list 1, 2, 3, 4. What's C's ID? It's this one. If I just say D equals C, as we know, pardon me, same location in memory. Not good. It's going to mess up my original list. But if I say D equals C, take the slice from beginning to end. Now remember, when we talk about accessing lists using this slice technique, using this colon, if there's nothing before the colon, that means start at the beginning. If there's nothing after the colon, that means go all the way to the end. This will copy every element from beginning of N to C into D. Now, what's the ID of D? Now, D is a different location in memory than C. And so D.append 5, D, C, I did not change my original list. So if you know in your programming that you do not want to modify your original list, if you only want to work with a copy of it because you're going to do something and change it and you want to keep the value of your original list, you can make a copy using a slice. Okay, you can also use the list constructor, E equals list C. E is 1, 2, 3, 4. ID of E is yet again something different. E is not the same as D. E is not the same as C. E.append 6. E, haven't changed C, haven't changed D. Okay. So those are two ways you can make a copy of the list and preserve the original so that you do not muck it up unintentionally. Okay. So a lot of times you're going to want to preserve the original and just work with a copy. So if you mess it up, if you change it, you don't care. You've still got your original. These are two different ways you can do it. Okay. So these are called a deep copy. When you hear the term deep copy, make a deep copy of a list. Here are two different techniques that you can use to make a deep copy of the list. Either use the list constructor or use a slice of the whole list to copy all the elements into a new object, and that will make a deep copy. A shallow copy does not, a shallow copy is when we say D equals C, and that doesn't give us everything we need. A shallow copy is one where we can still mess it up. Okay. I give another programming example where I've got a 2D list, and that gets uglier. And so we don't focus on that a lot in this class, but I do want to illustrate it. A is a list of lists. A is a 2D list. Okay. B equals A. ID A, ID B. They're the same location in memory. If I change B, I'm going to change A. I don't want to do that. So let's use one of our deep copy techniques to show how we're going to do to make a temporary copy that we're not going to fool with. Okay. So B equals A from beginning to end. ID B. B is now a different location in memory. We're good. But what about A sub 0? What about the ID of A sub 0? Where do I find that value? Interesting. Now, what is B sub 0? Where is B sub 0? Wait a minute. I got a problem. A sub 0 and B sub 0, that list is the same location in memory. Even though the big lists A is here, B, ignore that, is here. Those are different, but their components are the same. Okay, and so now if I change B 0, 0 to 1 million, now what's B? What's A? Whoops. The lesson there is this. If you're making a deep copy of a 1D list, the constructors that we've talked about, using slices, using list, will work perfectly. You'll get a true deep copy, and you won't mess up the original. If you are using a multi-dimensional list, if you are using a 2D list instead of a 1D list, those are not sufficient. If you want to make a true deep copy and not mess up A when you edit B, you're going to have to go through, cycle each of the component lists of A, and you're going to have to make a deep copy of A0, A1, A2. Now, we won't often do that in this program, but to make a deep copy, truly independent, you have to make a copy of all the components, not just the top level list. Okay. If the list is composed of int, strings, floats, and booleans, if you have a 1D list, right, then deep and shallow copies effectively work the same, and you could just use a list and you're good. When a list is made, when you have a 2D list, okay, to have a truly deep copy, you have to copy each component. You have to copy A0, you have to copy A1, you have to copy A2. You can't just copy everything. Okay. So unintended side effects. The point here is, if we're making a copy because we want to avoid messing up our original, then what we have to do is make a true deep copy. And if it's a 1D list, that's easy. And if it's a 2D list, we have to copy individual components. Bottom line again, what you need to take away from this lecture. Mutable, can be changed after creation. List, dictionary. I didn't show any illustrations, but take my word for it. I can if somebody's interested. I can create a dictionary, and I'll show that you can change the value of a dictionary. You can add a key. You can change a value. You can add a value. You can delete a key. Whatever. You will not change the location in memory because dictionaries are mutable. They can be changed after creation, and with all the good and bad that involves. Immutable, cannot be changed after creation. Ints, floats, Boolean strings, immutable. Complex types, lists, and dictionaries are mutable. If you add one to an integer, you get a new location in memory for that new value because you could never change the original. So mutable and immutable variables behave differently when you make assignments. Mutable variables, you can change the value of them without meaning to if you're not careful. You cannot mess up unintentionally an immutable variable. You cannot intentionally mess up an immutable variable because it can't be changed. If you added one to it or whatever, we assume you intended to do that. If you copied a new variable, that's fine. You intended to do that. Okay? But you can mess up your original list and you can mess up your original dictionary. Now, you may change it on purpose, as you do in Lab 7 with the function, as I did with the function in today's lecture. If you want to use the fact that it's mutable to change it on purpose, that's great. But if you don't want to unintentionally modify a list or unintentionally modify a dictionary, if you don't want to mess it up by using a copy, then you have to make a true copy of your list, a true copy of your dictionary, and work with that. That is what you must take away from this lecture. And in terms of the test, which is 2 weeks from today, what am I going to ask you? Well, I might ask you which of the following is an immutable variable, or which of the following is a mutable variable. I might have a program where I change a value of a list in a function and ask you if that changes the value of the argument. I might do that with a list and with an integer to see what changes and what does not change. Okay. That's really what you need to know. But now you can, if you had a question about what that issue in Lab 7 meant when it said, oh, don't worry about returning the dictionary because dictionary is immutable, this is exactly what it meant. Because when we're dealing with a function call and an argument parameter, we're dealing with the same location in memory. We can change it, so we don't have to return it. We can still change it anyway. That's what Lab 7 meant. Make a copy. That's really what you need to know in terms of the question, in terms of any possible test questions, in terms of understanding for program. You need to know you have to be careful with function calls, copies, assignments. If you want to work with a copy, make a copy. If you want to work with the original, you can go with a shallow copy and you're okay. That is all I had on the agenda for today. I still have 10 minutes. If anybody has any questions about the project or the labs or anything, I'll be happy to take them now. If you don't have any questions, you can drop off. Good luck. I'll be available if you have any questions coming up. Submit the design by tonight if you haven't already to the directory proj1_design all caps. It's submit CS201 proj1 design all caps and then your design, and be working on your code. Thank you. Okay. All right.
Hi, Professor.
Hey, what's up?
Hey, so I do have a question about the lab today.
Sure.
So I think I'm on the right track with it, but
Okay.
it's just sort of what was it? I guess it's